Hi, this is the basic principles of hemodialysis part 2. Hemodialysis clearance of solids. In clinical setting, the removal of a solid is measured in terms of clearance. The term being defined as the volume of blood or plasma from which the solid is completely removed in unit time, which is defined by milli per minute. Solids are removed continuously from the blood side to the dialysate side on the whole length of the dialyzer. During transient, across the dialyzer, most solids are removed from plasma water, about 93% of blood volume, depending on plasma protein concentration. The clearance of solid decreases as the hematocrit increases, since the plasma volume decreases. There is difference between the manufactured data and in vitro testing from the actual data in clinics, which is in vivo testing. In hemodialysis clearance of solids, in the body, we have generation of solids, which generates slowly, then transport within the body. Equilibrium, once generation is happened, it starts slowly enough for equilibration to occur between the extracellular, interstitial, plasma, and the cellular water. While on dialysis, during hemodialysis, blood levels fall sharply, but blood re-equilibrates as urea is recruited from the body. During hemodialysis session, clearance happened by removal of solids through diffusion, convection, and adsorption. Equilibrium within dialyzer between the plasma water and red blood cells is variable. As blood passes through the dialyzer, solids are removed from red blood cells to plasma with variable degrees. Equilibrium again within the body. So during hemodialysis, blood levels fall sharply, but blood re-equilibrates as urea is recruited from the body. There is a difference from the in vitro using aqueous solution from the in vivo using whole blood. For example, measuring urea in vitro is nearly as in vivo because urea equilibrates faster from red blood cells to plasma inside the dialyzers, while creatinine has very slowly equilibrated, so we can find that 20% drop of clearance from the manufacturing data. Hemodialysis clearance of solids by diffusion can be calculated by the following formula. While K is the clearance for a given solid in milli per minute, QP is the blood flow rate milli per minute, concentration of the blood inlet of the given solids minus concentration of the blood outlet of the same solid and divided by the concentration of the blood inlet. For example, if we are measuring clearance of urea, we have to multiply the blood flow rate, concentration of urea, blood urea, in the blood inlet, minus concentration of urea at blood outlet, and divided by concentration of urea in the blood inlet. When measuring the hemodialysis clearance by convection, as convection depends on the ultrafiltration rate. So we have here to put the QUF. So convection pipe clearance depends on the ultrafiltration flow across the membrane, as well as the membrane sieving coefficient for a given solid. Some definitions are overlapping. When we are talking about dialyzer flux or permeability, the flux measure of the ultrafiltration capacity, while permeability measure of the clearance of the middle molecules, example beta-2 microglobulin. General correlation between flux and permeability happen, while efficiency depends only on the urea KO value. We have low and high efficiency are based on that. Low efficiency has KOA value below 500 milli per minute, while high efficiency has KOA value above 600 milli per minute. Solute removal during hemodialysis depends on the solute molecular weight. Smaller are faster and better. Medium-sized is less. Either it's a free from protein bounded, which removes faster, while hardly removed from the blood if it's protein bound. Body distribution as well. In the intravascular compartment or in the intracellular or interstitial compartment. And as well hemodialysis kinetics. Example, diffusion, convection, and the solute flux index. In high flux dialyzers, the sieving coefficient refers to the amount of solute removed by convection. The term is S, referred to sieving of the solutes, which is equivalent to concentration in the ultrafiltrate divided by concentration in the blood. A membrane cutoff is defined when the sieving coefficient of a certain solute is below 0.1. In this graph, you can find the difference between the low flux sieving and the high flux sieving coefficient and the glomerular basement membrane. In low flux, the molecular weight could be removed is very small. While in high flux membrane, the molecular weight that could be removed is better and approaching the glomerular basement membrane. So clearance equals the rate of removal divided by the mean of inflow and outflow concentration. Rate of removal per minute equal blood flow multiplied by the inflow concentration minus outflow concentration. The difference between the inflow concentration of a given solute minus the outflow concentration of the same solute multiplied by the blood flow. While mass transfer area coefficient KOA value is a product of the overall mass transfer coefficient KO for a given solute multiplied by the dialyzer surface area and expressed as milli per minute. Factors influencing low molecular weight solid clearance during hemodialysis. Either dialyzer-related factors, dialysis-related factors, or patient-related factors. For example, dialyzer, surface area, membrane type and its diffusive permeability, membrane porosity, dialyzer rheology. In dialysis station, QP, QD, and dialysis time. While in patient-related factors, vascular access, recirculation percent, and patient hematocrit. Clearance by diffusion in dialyzer depends on concentration gradient, the blood flow rate, the dialysate flow rate, direction of blood and dialysate flow, molecular weight of solid, shape, size of molecule, and membrane property, surface area, number of pores, size of pores, distribution of pores, and the thickness of the membrane. Thinner membrane has higher diffusive permeability. There is a difference between high-performance dialyzers and high-flux dialyzers. High-flux dialyzers have higher middle molecule clearance, independent of efficiency, while low-efficiency dialyzers have small, lower solid clearance, independent of the flux. So high flux has middle molecule clearance, low flux has lower small solids clearance. Increasing the blood flow relationship between dialyzer and the blood flow in urea clearance while using high efficient dialyzers. You have up to a limit improving in the urea clearance. Increasing after 350 milli per minute is not linear. So we have here improving up to a limit. Then the curve is limited by simultaneous increase in the blood flow and the clearance value. Also, clearance depends on the solid molecular weight. Small solids like urea has higher clearance value with increasing the flow rate, while bigger molecules like inulin, which equal 5,200 Dalton, has nearly flat clearance value with variable QP. Also, the dialysate flow rate can improve the clearance value. At blood flow rate below 200 milli per minute, no difference exists between the dialysate flow and the blood flow in urea clearance, because equilibrium in urea concentration between blood and dialysate is readily achieved. When the blood flow rate is high, above 300 milli per minute, the higher QD maintains a higher concentration gradient for diffusion of urea, and therefore the urea clearance rate is higher. Causes of low clearance value despite use of high efficient dialysis: vascular access related, low blood flow, high circulation rate, time related factors, not adherent to prescribed dialysis time, failure to adjust the prescribed time due to repeated alarms, hypotension episodes, and the dialysate bypass. There is an important way to improve the clearance is by better blood and dialysate flow geometry. The blood to dialysate matching is important to increase the clearance. Blood flow and dialysate flow matching improve the overall clearance value. In straight fibers inside the dialyzer, there is what is called dead areas, where blood is not matched with the dialysate flow, and so this area has no clearance. Also, in dialyzer, the blood flow in the middle, in the center of the dialyzer, is higher, while the dialysate flow in the periphery is higher. So in the middle of this dialyzer, there is a mismatch between the blood and dialysate, while in the periphery, the reverse occurs. We have much dialysate more than the blood. So dialyzer geometry to enhance the performance and improvement of blood and dialysate flow matching can improve the clearance. We can use one of two. Either use of spacer yarns between fibers, separating adjacent fibers from each other, and these spacer yarns consist of multi-filament threads integrated into the fiber bundles, and this improves the dialysate distribution through the dialyzer. Or to use the microindulation, which is the fibers are not straight, indeed it's microindulated. And this microindulation technology for better blood and dialysate matching. We can see here in the three graphs the typical blood and dialysate mismatch, and this improve with spacer yarns and much improvement with microindulation technology. The Japanese classification of a dialyzer permeability depends not only on the solids, small molecules, but on the beta-2 microglobulin, the middle molecules, and classified from 1 to 5, with 5 has the highest clearance value for beta-2 microglobulin. Another classification of high flux depends on the ultrafiltration rate, above 20 milli per millimeter mercury per hour, and beta-2 microglobulin sieving coefficient more than 0.6. Remember that dialysis membrane is not a one-way street. There is increasing flux risk. Endotoxin transfer is higher with high flux, as well albumin loss. That's why you have to use ultra-pure dialysate when using the high flux dialysis. Thank you very much.